Greetings, fellow humans, and welcome back to Arduino for Dummies. This is Chapter 8. It's called Motion and Sound. We're going to be trying out some new components that we haven't used before in this one. We're going to have a DC hobby motor, we're going to have a servo motor, diodes, transistors, piezo buzzer, and a light sensor. That's a lot of stuff to pack into one chapter, and it's going to be a long one. I think this is probably going to take close to an hour, so settle in and get yourself comfortable and let's get to it. These are the supplies we're going to need for the motor sketch. We'll need the Uno, the breadboard. The book calls for a 2.2K resistor. I don't have one of those. So the next size up that I do have is 5.1K. So I hope that's going to be all right. We're going to need a bunch of jump wires. I like to try and color code them the way the book recommends. So the ones that are the power source are red. The ones that are heading to ground are black. And my signal wires are a different color. I just grabbed a white one because it's longer. We're going to be using a hobby motor. So this is a little DC motor. Those are the connection points there. We're going to use a transistor. That's this little guy with the 3 prongs. I'm going to zoom in on this. Because these are really, really tiny. This is a diode. A diode only allows electricity to flow through it in one direction. So the reason they say that's important in this sketch is that with a DC motor, when it starts to slow down after you turn the power off, that momentum can generate some electric current from the motor. Or if you manually turned that the opposite direction, it can send an electric current back through your circuit where you don't want it to go. And if that's allowed to flow into certain places, like one of the pins on the Uno, it can cause damage. So the purpose of the diode is going to be to prevent any current from flowing in the wrong direction on the circuit. So I'll try to diagram this out in a minute. But these are all the bits and pieces that we're going to need. So I had to put mine under a light to be able to read it, but apparently mine is a 2N2222A type resistor. I also had 2 other types in my kit, but I'm not going to be using them right now. I also had these transistors. The book says there's 2 types, and I have some of each, NPN and PNP. I don't understand what the difference is yet. I don't think it's relevant because the book doesn't really talk about it in this chapter, so for now I'm not going to worry about it. This type is similar to the type that the book recommends we use, so that's what I'm going with. And my kit only came with 1 type of diode, so that's what I'm going to have to use. 1N4007. I don't know what that means, but hopefully this one will get the job done. Here's the diagram for the motor sketch. So in this one, we're going to be looking at a DC motor for the first time, diode, and transistor. So how this is supposed to work is we hook up one end of our circuit to a 5-volt source on the Arduino. The full 5 volts will go through the DC motor and make it spin. The transistors down here, that's going to be like an electronic switch where we can turn the whole circuit on or off. And after it passes through the transistor, it goes back to ground. So the other thing we've got in here is the diode. And The book didn't really explain why that's there very well. So I went to the sparkfun.com website, and they show a similar example where the diode acts sort of like a safety. It's like a safety circuit that goes around the motor. The other thing they talk about is how a motor can generate its own current. So I think the diode is here to give the current another path to flow where it can go back into the motor rather than go off somewhere where it could do damage after we've shut off the current. Anyway, this will probably make more sense later, but for now, we'll just take their word for it that having the diode here makes the motor safe. So the transistor is the other big piece of this. Transistor has 3 pins on it. Let me hold one up here. They're just tiny. The ones that we're using will be tiny. So there's a collector pin, which is where the current enters, and there's an emitter pin where it exits. And in this example, from the emitter pin, it's going to go back to ground. And in the center is a base pin. The base pin is what you use to open or close the circuit in the transistor. We're going to hook up the base pin on the transistor to pin D9 on the Arduino. And then we're going to use code to open and close the circuit on the transistor. The book recommends you use a 2.2 kilo ohm resistor in between your signal pin and the base pin on the transistor. I didn't have that exact amount, so what I've done is I wired in a 2K resistor and a 220 ohm resistor in series, and that should add up to 2.22, which is really close to what they recommend. So I'm going to jump right into showing you how it works, and then we'll take a look at the code, and then I'm going to zoom in on this and look at how it's wired up. Okay, so first step, I'll upload the code. So here's a little hobby motor. The way the code works, oh, there we go. It will spin the motor for 5 seconds and then open the circuit for 5 seconds. And I do think, I think I've got something loose here because it seems to be a little twitchy. I'm going to hold it up for now. There we go. I stuck a little document tab to that so you can see it spin. Wait 5 seconds and spin. So that's all it's going to do. And it always spins at the same speed. The next sketch in the book is going to show us how to do variable speed. Okay, so let's take a look at how this works. And for now, that's that's going to get kind of annoying. I'm going to just pull the power on the Arduino for a minute. Okay. So the code's very simple. I don't know if you noticed on the board, but every time the motor would spin up, that little tiny LED with the L next to it would also light up. I just did that so it would be easier to diagnose any problems with the circuit. So in the setup, we've seen this in sketches before. We set the pin mode to output. I'm using the serial monitor on this one, so we've seen that before as well. So every time through the loop, the first thing it will do is turn on the motor. So the motor pin is D9. It sends the high signal to, I know it says motor pin, but it's sending the high signal to the transistor base pin. It also sends a high signal to the LED on pin 13. And then it will do nothing else for 5 seconds. After 5 seconds, it will send the low signal to the transistor base pin and the low signal to the LED. And it will stay that way for 5 seconds. And then it will just keep doing that over and over. So let's look at how this is wired up. First, I'll mention that I've soldered 2 bits of wire onto this hobby motor. The contact points are really tiny on it, and I found that was kind of a pain to work with. So having some longer bits of wire attached just makes it easier. So right here is the 5-volt source pin on the Arduino, and that comes over to the breadboard. And you'll notice on the breadboard, on the outer bands on each side, there's one band that's marked with in red with a plus, and then a blue one marked with a minus. So that's where you can put your power source into the plus, and you can put your ground wires into the minus. And unlike these ones in the middle that everything that's in the same row is connected, on the outer bands everything that's in the same column is connected to each other. So we get our power source over to the red band on the side, and then I plugged another jump cable in here. Then the current will travel over this way. It goes, let me zoom in a little bit more. So the power, the current is flowing in this row. I've got the diode here, but the little band is on this side. So the current can only flow from right to left. So the current will exit on this side. So it continues this way. It will go through here into the motor. Then it will exit the motor on this side. This whole row is connected to the collector pin on the transistor. It will pass through the transistor and exit through the emitter pin. That goes to this wire, and then that goes back to the ground column on this side, and then this is also connected to it, and the black wire will take it back to the ground pin on the Arduino. So the other thing that's important here is from pin D9, let me scooch that in a little bit. So from pin D9 on the Uno, this yellow patch cable comes over here. I've got my 2 resistors in series that adds up to about 2.22 kilo ohms of resistance. And then, oh, that's in the way. Then that's connected to the center pin on the transistor, which is the base pin. So that is how we're using pin D9 to use the transistor like an on-off switch. The next sketch is called motor speed. And conveniently, this one has exactly the same wiring as the last one did. I put a little piece of tape on the end of my motor so it can spin a little easier. In the last sketch, I had this big flappy document tag and it was kind of getting the motor stuck up. These little motors are not powerful at all, so the least bit of resistance can stop it. So the only difference between this sketch and the last one is going to be the code. So let's take a quick look at what the code does first, and then I will upload it and we'll watch it work. So in this one, we are going to be ramping up the speed of the motor using one of the pulse width modulation pins. And we were actually using one before. We were using pin number 9 on the Uno. But we were using it in digital mode, and this time we're going to use it in analog mode. So the setup for that is the same. We are setting pin number 9 to output mode. And down below we're using 2 for loops to start from a minimum value and then slowly ramp it up to the maximum. So if you remember from other sketches where we used PWM, the maximum value you can use in the analog write command is 255. So that's going to be the top of our for loop. And then down below, well, let me talk about this one first. In this for loop, we start from the minimum value and go up to 255. Then when that one exits, we will hold that maximum value for 5 seconds. So the motor should be going full speed at that point. Then after that 5 seconds, we'll have a for loop that goes from 255 and slowly ramps down to the minimum value. And after that finishes, then it will stay at the minimum for 5 seconds. So in the book, they have the minimum value as 0. And they do mention that at the lower values, you might just hear a hum from the motor and it won't actually turn. And that's definitely true. But I found that you really have to ramp it up a lot before it moves at all. And for me, that magic value was a PWM setting of around 150, which is more than halfway from the minimum to the maximum. So these things really need a bit of a kick to get them started. So I'm going to upload it, and I'm going to upload it with my magic value as the minimum so you can see it working nicely. And then I'm going to change that to 0 so you can see how long it will sit there just buzzing but not actually doing anything. So let's upload this guy. And I'm also going to open the serial monitor, which really helps to know what's going on. All right. Sorry about the vibration. I had to wedge the motor between a couple things because it vibrates a lot and it will vibrate right off the desk if I don't. Okay, so this is at my minimum value, and now it's going to slowly speed up to the maximum again. That's the maximum, and now it's slowing down again. So the example in the book, they ramped it up from 0 to the max pretty fast, and I found that wasn't very fun. I like to watch it slowly ease down. Like that. Seems more controlled. All right, so I'm going to close the serial monitor and I'm going to change that one value. So I'm going to set the minimum to 0, just so you can get a sense of how much time it spends trying to move but not able to at the low voltages. I'm going to bring the microphone in really close. It's just a very low hum. All right, so only point I was trying to make there is that the lower voltages sometimes can't move those DC motors at all. So, yeah. Next up is the motor control sketch. This one builds on the previous sketch. This side of the diagram is the same, and so is all the wiring on here. We've just added a little bit to it. So over on this side of the diagram, you'll see that we've added a 10K variable resistor, also known as a potentiometer, and we've got that hooked up to the analog 0 pin. So what this is going to do is the variable resistor will replace the code that we were using to make the motor speed up and slow down in a loop. Instead, we will turn the knob on the variable resistor and manually adjust the speed. So let's take a look at how that works. So if we take a look at the wiring, most of this is the same. The addition is the potentiometer right here. That is on its own circuit, but it does share these the power band and the grounding band on the breadboard. And it feeds off the same 5-volt source on the Arduino, and it grounds to the same grounding pin. So the only thing that is different here is the orange cable that goes to the center pin on the potentiometer, and the other end goes into the Arduino on pin A0. Okay, I'm ready to spin this thing up. So I don't have a knob for the potentiometer, so I'm just kind of twisting the dial with my fingers. It's going to make it a little bit hard to see on the camera. I'm going to zoom out a little bit because we also can't see the motor right now. There we go. Try to bring everything in as tight as I can so you can still see it. So again, I've got the little piece of tape on here, so when it starts to spin, you should be able to see that. Right now, I've got the potentiometer turned all the way to one side, so it's at its minimum setting right now. And the way I wrote the code is when it's at the minimum setting, it will turn the power off completely to the engine. And as soon as it gets turned up even one notch, it will start to spin it. So if you watch the last sketch, I figured out sort of the magic value for my equipment where the PWM setting is just high enough to make the motor turn. And that's what I'm using. As soon as you turn this up even a little bit, it will use that magic value. And then after that, when you turn it up, it should be a linear increase up until it gets to the maximum. So let's give it a little turn. Here we go. Oh, and it's spinning just a tiny bit. And now I'll turn it back off. And now on just a little bit again. When it gets that, oh damn, that loose connection is driving me crazy. I think my left solder point is the problem. It seems whenever I move that, I'm in for trouble. Yeah. I am terrible at soldering. I've got another video up that shows just how bad I am at it. It's kind of embarrassing how bad it is, but I need some practice. Anyway, let's turn that off and then on and off. I'm just giving a little twist on the dial. Now I'm going to turn it up more. It doesn't really make much sound, so I don't even know if you'll be able to hear it on the video. I'm going to turn it all the way up now. Yeah, it sits a little bit better on this. This is an old laptop battery turned upside down. It's kind of grippy on the bottom, so it keeps this thing from vibrating off the desk. All right, I'm going to open up the serial monitor. Oops. I made it pause for a second. So the readings that it gets from the potentiometer are not very accurate. So in the serial monitor, it looks like it's going crazy getting a whole bunch of different readings, but in reality, I'm not touching this at all. It's just not a very accurate way to send signal. Every once in a while, if I turn it to just the right spot, it'll hit a sweet spot where it gets a steady reading. Oh, I thought I had one there. No. There's one. It's getting a steady reading of 578. Ah, shit. Yeah, that's pretty good. All right, now I'm turning the motor almost down to the minimum that it can spin. And if I turn it down much more, I'm going to reach the minimum value on the potentiometer. And what I did in the code was I said if the potentiometer gets down to its minimum level, then just cut the power to the motor completely. And that's what I've done. So let's close the serial monitor and take a look at what the code does. So like the last one, we've defined the transistor base pin as pin 9. We're using it in PWM mode. The potentiometer pin is new. We weren't using that in the last one. So that's using the analog 0 pin, and that's in input mode. You can see that there in the setup method. And there's our transistor base pin in output mode. This line is just to set up the serial monitor. And this is my magic number for the minimum PWM setting that will actually move my hobby motor. It doesn't necessarily mean that your motor will need the same value. These things are probably all different. But for mine, that's how much juice it needs in order to move it at all. And it's only got a tiny little piece of tape on it, so there's nothing really holding it back. All right, so down in the main loop, I keep track of the last motor value. So every time it goes through the loop, I will set last motor value to whatever the current value is. And then the next time through, it's only going to write out to the serial monitor if the value has changed from the last time through. Now, this wasn't in the example from the book, but I like this. What I'm doing here, I'm using the modulus function in C. What I'm saying is, if motor value does not divide evenly into 5, then take the remainder and subtract it from whatever motor value is. So I'm basically rounding it down to the nearest multiple of 5. And I did that to try and make the adjustments on the potentiometer a little bit less jumpy in the serial monitor. It helped, but it's still a little bit jumpy. If I made this number bigger, it would smooth it out more, but then you would have less range, and I didn't want to round it too much. So what we're saying here is, if the motor value has changed from the last time through the loop, write some logging to the serial monitor. And if it is above the minimum value, then we will set the motor speed to that value. Otherwise, if it is at the minimum, just turn it off. So if we're setting the motor to a certain speed, we use analog write. If we're turning it off, we just use digital write and send it the low setting. We don't need a range of values for low. I think low is just 0. An alias for 0. And I also print in the log motor off when I do that. The book says that you should have a delay every time you go through the loop, and I think that is in there so that it's not trying to read so quickly from the potentiometer. And since I'm doing serial monitor output, it's also good to keep that from getting flooded too much. That is all. Here's what we need for the sweep sketch. This is the first one where we'll use a servo motor. So unlike the motor in the last sketch, which would just spin when you apply current to it, this one is meant for precision movements. So you tell it what number of degrees to turn to, and it will move to that position and stay there. I did a quick Google search and I easily found the spec sheet for my servo. The spec is really short. It's only 2 pages, but the only thing that's really important to me is this part where it tells you which pin is for which. So orange goes to the PWM, and in the book they're saying we should use pin number 9, so that's fine. And red is where the 5-volt power source will plug in, and brown is where the ground wire plugs in. I've got everything set to go here. I screwed one of the fins on the top of the servo so I could attach something to it, and I decided just to use this little eyeglass repair kit screwdriver. So a minute ago we took a look at the spec for this servo motor. I just gotta lay it on its side. And we saw that the orange wire on the servo is where the PWM connection should go. So I'm gonna take the yellow wire and plug it into pin number 9 on the Arduino. The brown one is the ground wire, so I'm going to plug that into one of the ground pins on the Arduino. And red one is the power supply, so that's going to go into the 5-volt pin. And that is this one. Oop, I got a little twitch out of him. Okay. So first I'll show you the the stock sweep sketch that comes with the Arduino development environment. So you go to File, Examples. You have to scroll down a bit toward the bottom, and there's one called Servo, and under Servo you will choose Sweep. And this is what you'll get. And this one works. In the loop, it will sweep from 0 to 180 degrees, and then go from 180 degrees all the way back to 0. And it just does that over and over again. And that's fine. I did run that one earlier, and it does what it should do. But my problem is, when this thing came in the package, the fins weren't attached to the top. So I didn't really know what position it was in when I took it out of the bag. So I kind of had to guess, and I guessed wrong. It was way off center. So in my modified code, the first thing it does in the loop is it will go to the 90 degrees position, which should be right in the middle of its range. And I put a 5-second delay, which is enough time for me to pull the power out of the Arduino. And with the power out, I took the fin off, I adjusted it to be centered, and then I put the screw back in it, and then put my little death ray on top. So it should be almost centered. I still had a hard time getting it right on center. There's grooves in this top attachment piece, and it was hard to get it right on, but this is just for fun anyway, so it should be good enough. All right, so I'm going to spin this up. So what the code should do is set it to 90 degrees, so it should be pretty much dead center. Stay there for 5 seconds. Then it will move to 0 degrees. I think that's all the way in this direction. It will stay there for half a second, and then it will do the full sweep across and back. And when it gets all the way back to 0, it will stay there for half a second. And then it will start the loop over again, so it will go back to 90 degrees and stay for 5 seconds. So I'll let it run through a couple sweeps so you can see what it looks like. Make sure I'm in frame here. Yep. And this thing does not stand up very well, so I'm gonna have to hold it. Oh, that's promising. Oh yeah. I'll put the microphone closer so you can hear that robotic sound. So here's the setup for the knob sketch, which is the next one. This is based on one of the examples that comes with the Arduino kit. And I'm going to make a few tweaks to the code, but it's a pretty simple one. So in the last sketch, we used code to just make the servo motor sweep back and forth from 0 to 180 degrees. In this one, we're going to wire it to the knob on the variable resistor. So as we turn this, this will turn with it in real time. So we need to use a breadboard because we're sharing the 5-volt power source and the ground pin with the variable resistor and the servo. So we're going to use the plus band on the breadboard for the 5-volt source, and the blue minus band will be the path to ground. So here's the 5-volt pin on the Uno. It comes over to the red plus band. Here's the black ground wire. Oh, I should zoom in. Sorry about that. There we go. The ground pin on the Uno is connected to the blue minus band. So we've got the variable resistor wired into those, and the center pin on the variable resistor goes over to analog 0 on the Uno. We've got the power source and ground wires for the servo wired into these bands, and we've got an orange signal wire going to pin number 9, which will be in PWM mode on the Uno. All right, I've got everything wired up, the code's uploaded, and it's ready to go. I had to put a piece of tape under the servo to hold it in place. These things are really lightweight, so just the motion of moving the top usually knocks it over. So here we go. When I turn the knob, it's going to move with me. Look at that. It's really responsive. Cool. And this one was so easy to wire up compared to some of the other things we've wired up. But we have to remember that these little servo motors do have some intelligence built into them, so that does make things a bit simpler from our end to hook them up. That's it. Oh, yeah, I almost forgot to open the serial monitor. So in my code, whenever I send a signal that changes the position, it will write a line to the serial monitor. So now it says it's pointing to 179, which is as far that way as it can go. And now I'm going to turn it as far as I can go the other way. But I do have, you probably can't hear that low hum, but it's having a little trouble. And you can see on the serial monitor that it's very jumpy. My variable resistor seems to not get a solid reading when I turn it all the way in one direction. So that means I can't consistently get this all the way to 0. And also when I turn it to 90 degrees, if I can get it, there we go. It's not pointing straight, but that's my fault for not screwing on this little plastic piece on top. I thought I had it centered, but I was off a bit. So the servo is doing its job. That was my fault. I could always pull it off and center it again, but these things feel really fragile. It's all plastic, so I don't want to keep taking the top off. I figured eventually it's going to break if I take it off too many times. Anyway, I'm loving this. That is fun. And I'm sure there's going to be lots of other applications for servo motors in my future. But for now, that's the end of this sketch. Fun stuff. Oh, wait. I was about to shut it down and I realized I haven't even talked about the code. All right. I'm going to close the serial monitor. All right, let's take a quick look at the code. The base example is here under examples, servo knob. That's the basic one. I just made some modifications to that one for mine. So we declare a constant for the knob pin, or it's the potentiometer pin. And like in the last sketch we did, the servo is connected to pin number 9 in PWM mode. So in the setup, we have to associate pin number 9 with the servo. The servo library knows how to read the PWM settings that we send through to it, so that makes it simpler on our end. And I've also set up this serial monitor here so that we can write out to it. Okay, I keep track of the servo position every time through the loop, so that the next time it comes through I can see if it's changed, and if it has, I will send the new position to the servo and then write a line out to the serial monitor so I can see what's going on. Here's the analog read where we read from the variable resistor, and we get a value between 0 and 1023. And then we'll use the map method, which we've used in several sketches before, and we're converting the range of 0 to 1023 down to 0 to 179, and this represents the range of positions that the servo can move to. And here's where we set the new position if it's changed from the last time through the loop, and then I save it, and I set up a delay of 50 milliseconds every time we go through the loop so that it gives it time to move to the new position smoothly before we send it another signal. That's it. This one's pretty simple compared to some of the others we've done, but it's a cool sketch. It's fun to have that thing moving around in real time as I turn it. Fun stuff. The next sketch is called Tone Melody. And in order to make tones, we're going to use this little guy. It's called a piezo buzzer. The only other stuff we need is the breadboard, 2 jump wires, and the Uno. So the piezo buzzer has a positive and negative lead on the back, and inside this case there's a little disc. And what the book says is, if you switch between a voltage and ground, the piezo bends and generates a tick sound. If this happens fast enough, these ticks turn into a tone. So we don't need to deal with all that low-level stuff. There are functions in the Arduino kit that will do that for us. So let's jump right into it and see what we can do. Okay, everything's wired up. It's very simple. The piezo buzzer is pushed into the breadboard. On the side that has a plus on it, I've connected this red wire, and the red wire goes to pin number 8 on the Uno. On the other side of the piezo buzzer is the black wire, and that goes to a ground pin on the Uno. I've already loaded up the example code for Tone Melody. If you want to find it, it's under File, Examples, Digital, Tone Melody. So here's what it looks like. It includes this file called pitches.h, and in the pitches.h file it's got a whole bunch of different notes that are already defined if you want to use them. I'm not going to worry too much about that right now. It's declared 2 arrays up here that are the same size. It looks like the first array contains the notes that we want to play, and the second array contains the duration of how long each note will play for. And yeah, so we're looping through each item in the 2 arrays. It calculates the duration that goes to this tone function. So I'm assuming this tone function is built into the Arduino, the core Arduino IDE. Alright, seems pretty straightforward. I'm just going to run it. I don't want to spend too much time on this sketch. Let's upload it, and we should hear the tones play once. Put the microphone down next to it. That's it. That's all it does. They put all the code in the setup method, so it will only run once. And if you look down here at the loop method, that doesn't do anything. So that's why it only runs once. If you want to run it a second time, I'll move the mic down here again. You can press the little reset button on your Uno. It's in the upper left-hand corner. That will make your code start from the beginning again, which also always begins with running the setup method once. So I'm going to press this now. That's it. The next sketch is called Pitch Follower, and this one combines a light sensor with the piezo buzzer, and as you pass your hand over the light sensor and change the amount of light it's receiving, that will in turn change the pitch of the sound played by the piezo buzzer. So we also need the book calls for a 4.7K resistor. The closest one that I have to that is 5.1, so I don't think that's going to make much difference. And this will be the first time we use a light sensor. And I had to dig around in my kit to find this. I didn't even know what this was for until now. I believe the proper technical term is photoresistor, and that's what it was called on the inventory of my beginner's kit. And I got two of these. They're really tiny, as you can see. The ones I have really long legs on them. So let's start building and see what this thing does. Here's the diagram for pitch follower. Like in the last one, we've got the piezo buzzer connected to pin D8, and then the other end goes to ground. In this one, we've also added a separate circuit. It's connected to one of the 5-volt pins on the Uno. It goes into the photoresistor. Then after that, it is connected to pin A0, so it can take analog readings from the photoresistor. In that circuit, we have a 5.1K resistor, and then that goes back to ground. Got everything wired up. We've got one wire that comes from the ground pinned on the Uno to the ground band on the breadboard. The piezo buzzer is hooked up similar to the last sketch. We've got its power coming from pin 8 on the Uno, and then it goes to the ground band on the breadboard this time. On our separate circuit, we have power coming directly from the 5-volt pin on the Uno to one end of the light sensor. It passes through the light sensor, and on the other end, we have a signal wire that goes to analog 0. And in that same column, we have one end of the 5.1K fixed resistor. When the current passes through that, it goes into this ground wire and goes back to the ground band on the breadboard. Okay, I have not uploaded the code yet. As soon as you do upload the code, it starts buzzing, and it's kind of a fun sketch, but that buzzing sound gets annoying really fast. So let me show you. I'm going to put my mic down next to the piezo buzzer. All right, start uploading. I'll get the serial monitor ready to go. Now, if I pass my hand over the light sensor, it changes the pitch. All right, I'm going to shut that off. I'll just upload the blink sketch just to get that sketch out of the memory of the Uno. Whew. Not a pleasant sound. All right, let's take a look at the code though. So I define a constant for pin number 8, and that's the one that sends the current pitch to the piezo buzzer. I also set a min and max value for my light sensor. You'll want to set a different range for these. This is what worked for me right now in this room with the current amount of light coming in from the windows. If I did this at nighttime, I would probably do it with different values because the overhead lights would either be brighter or dimmer. It's hard to say. The only thing to do in setup is to get the serial monitor ready if you want to write out to it. Now, every time through the loop, we read the current value from the light sensor from A0. That goes here. Then in this next block, I'm saying if the value happens to fall below the minimum that I've declared above or is above the maximum, just cut it off, and that keeps it boxed in a range that I've defined. Then we write out to the serial monitor, and then we use the good old map method to convert our sensor reading from a range between min and max to a pitch range between 120 and 1500. These are the values that were in the original code, so I just left them as they are. Probably should have experimented with changing those. Maybe the sound would have been less awful, but probably not. So then every time through the loop, it is going to send the piezo the current pitch based on the light reading. And I believe that the last parameter to the tone method, the 10, I think that's a value in milliseconds of how long it's supposed to play the pitch. And every time through the loop, we do a 5 millisecond delay. In the original code, they only use 1 millisecond. I just thought I would give it a little bit more delay. I think this value is pretty much up to you, what you use. That's it. That's all it does. And this has been a long, long chapter, so thanks for watching all the way through, and I'll see you in the next one.